All right, I think we are ready to get started. So this is our 10 o'clock workshop, why Jezero Crater is the place for Mars 2020 sample return. So our panelists today, we have Ken Farley from NASA Jet Propulsion Laboratory in Pasadena. We have Briony Horgan from Purdue University. We have Michael Meyer from NASA headquarters, and Ken Williford from NASA Jet Propulsion Laboratory. So I'll turn it over to our panelists.
Well, thanks. I'm Michael Meyer, and why we're here is to talk about the site selected on Mars to send the next rover, Mars 2020. We've gone through a period well over 4 years, 4 workshops involving something on the order of 150, 200 scientists going through different places on Mars, narrowing down the field to what are the best places to go to meet the objectives of the 2020 rover. And the 2020 rover is going to look and study potential habitability and also look for potential biosignatures if there are any on Mars. It's going to explore the region to understand its geology, to understand its past. It's also going to be doing something that we haven't done before with a rover. Instead of having an analytical laboratory like we have on Curiosity, we're going to have a caching system. So this rover will cache samples for a potential future sample return. And then also it has a tech demo of in situ resource utilization. It's to prepare for future human exploration at Mars, and it's going to make oxygen out of the carbon dioxide atmosphere. But what I want to do is now we have gone through the general objectives for the mission. We now have the place where we're going to go, and so this is all about Jezero Crater and the great things that we can look forward to. The mission is launched, the window opens 17th of July, 2020. There's not that much time left, and arrives in Mars in February of 2021. So we're getting very excited. We now have the face of the place where we're going, and with that, I want to turn this over to, I guess I should have advanced this. Here's the rover, and it shows a fair amount of international collaboration. Things are working very well with our international partners, and we have the capability to pick samples that are going to tell us about the geology of the area, going to tell us about whether or not there are potential biosignatures there, and with that we can cache the samples. We'll learn a lot about Jezero Crater and the surrounding area, and also then have samples that could be returned back to Earth. So let me turn it over to Ken Farley, who's the project scientist, and he'll tell us much more about Jezero Crater itself. This works.
Thanks, Michael. Let's see, so I can drive with this too. All right.
I didn't drive with either.
How do you advance with this? I just advance with this. Okay, so I want to tell you why we are super excited about the recent decision that we arrived at, that we will go to Jezero Crater. So for the remainder of this presentation, we will tell you about the science that we can do at this site. I think the most important points that Michael made that drive the decision of the landing site that we are discussing are we are seeking the signs of life, and we are preparing a cache of samples for the first potential sample return from another planet. So these are really important objectives that dictated the decision that we came to. So the first really important thing, oh, that'd be great if you could do that. Okay. Next one?
Except for...
You can't do that. Okay. So at present, the surface of Mars is not a habitable environment. It's too cold, it's too dry. But it wasn't always that way. It is very clear that in the distant past, there was an abundance of surface water. And what you see here is an artist rendition of the site that we have chosen to go to, which is called Jezero Crater. And the blue is obviously indicating that it was once a lake. Can you advance? Thank you. And so what I want to talk about is the pathway that has led to Jezero Crater and the interest that we have. And I'm going to start at the beginning. Going back to the formation of the solar system. Of course, the planets formed 4.5 billion years ago. And one of the important geologic considerations in our landing site is the framework of the rocks that this lake was in. And the key features are shown on this slide here, where we have early bombardment by planetesimals being swept out of the solar system, forming Isidis Planitia, or Isidis Basin. So this is a giant impact basin. And this actually produced the structure, which will be very obvious in some of the images that you see going forward. The site, Jezero Crater, is actually located on the edge of the Isidis Basin. Next slide. So at that time, prior to about 3.9 billion years ago, there were a number of very interesting things going on. The early history of planets is not especially well understood. For example, if we try to study it from Earth, there is essentially no geologic record from this time period. Yet many of the rocks that we have available to us on the surface of Mars date from this era. And of course, this is the kind of thing that the InSight mission to Mars is trying to study at the present time. We want to know what it looked like in the distant past. For example, was there a magnetic field? Was there a convecting mantle? We presume that there was a thick atmosphere and abundant surface water and subsurface water. And the geologic evidence for that is overwhelming. So we want to understand those processes, and that's something that we can do both with the rover and with the samples that we bring back to Earth in the future. So we start out with the Isidis Basin, and at that distant time, many people believe there may have been a northern ocean. A lot of surface water on the surface of the planet, possibly filling the Isidis Basin. And at about 3.9 million years ago, the exact age is uncertain, the Jezero impact occurred. This was an impact with a body that produced a crater that was something like 30 miles across. Next slide. So in addition to this framework of rocks that record the early geologic history of a terrestrial planet, this impact also exposed to us the deeper crust. It's hard to have access with a rover to the deep crust if you don't have something that exposes it. So one thing that exposes is an impact. But in addition, this provides us a first potentially habitable environment, which is that those rocks would have been hot when they were exposed, and they likely would have had hydrothermal systems circulating hot water through the rock. And such environments are very conducive to life on Earth. So this is the first habitable environment that the rover might be able to explore. And to talk further about the astrobiological potential which follows after this, I'll turn it over to Ken Williford, who is a Deputy Project Scientist for Mars 2020.
Yeah, okay. Okay, morning everybody. So now we're zooming back out to that regional view here where Ken was mentioning Isidis Planitia, Isidis Basin. This enormous impact basin, about 1,000 kilometers. So the distance across from Jezero Crater down to the other side of Isidis Basin is sort of the distance between here and Jacksonville. So imagine an impact crater that's that big. Things that large were only forming very early in the solar system's history. But on the northwestern edge there, you see Jezero Crater at a time, shown here at a time when there would have been abundant surface water flowing into this crater, generating a lake as the water came in through a large network of channels that you see here, shown, indicated as inflow channels. So we had water flowing in from the northwest. But then one thing that's very interesting and unique about Jezero Crater relative to other crater lakes on Mars, including Gale Crater, where Curiosity is exploring now, is we have good evidence that there is an outflow channel as well. So clearly Jezero, for some period of time, was operating as a very dynamic open system as a lake there. One of the key questions, obviously, for us is not so much was there water there in Jezero Crater, but where did that water come from? So we know the water flowed across the terrain northwest of Jezero, but did it emerge from some of the events, like Ken said, heated crust and water bubbling up from springs and then flowing across the surface and filling the lake? Or was it raining on Mars at some time and there was a water cycle similar to what we see on Earth today? Or is it all from ice or snow melt? And so these are some of the things we think we can hopefully make some progress on with Mars 2020. Now, for the next few slides, you'll see we've zoomed into Jezero Crater now. This is a cartoon of Jezero Crater showing you at the left the inlet channel, at the right the outlet channel. The water is flowing into the lake from the left and out of the lake on the right there. You see the delta form there, but we're going to add onto these images different little geologic symbols that will be indicated in the key down at the bottom right. And this is basically, we're going to build a geologic map here for you and show you some of the key geologic units or rock types that we'd like to explore during the mission. The first one is the one Ken talked about. So the actual physical structure of the crater itself is made of a very complex rock type that you might call an impactite, and that's just what's left over when you ram an enormous rock into existing crust, and it gets all jumbled up and chemically and physically altered. So very interesting, may preserve habitable environments, but also we could sample that impactite and get an age. If we return that sample back to labs on Earth, we could date the Jezero impact event, and that would, of course, be very useful to us as a maximum age for all that sedimentary activity that we see in Jezero, in the delta and the lake, and all that interesting evolution of habitable environments inside Jezero. So now going into the sedimentary units themselves, you see some sandy units in the little stippling, so sandstones and conglomerates, partly making up the delta. Sort of the top part of the delta is made of what we call coarse-grained delta deposits. So imagine sandstones, things closer to the river mouth. As you get further out towards the middle of the lake, you think about the muddy bottom of the center of the lake. These are the fine-grained delta deposits that sit down at the bottom of the delta. These are both scientifically interesting for different reasons. The coarse-grained stuff, one of the things we love about it is it integrates the geologic diversity of the watershed. Well, what does that mean? So all these really interesting rocks that Ken talked about regionally that represent the oldest Mars crust really exposed on the surface of the planet, those are integrated. Those are broken up by these stream channels upstream of Jezero Crater and roll down into Jezero as grains of sand. And in a sense, in one of our sample tubes, with 15 grams of sample, we would have thousands of little subsamples as grains of sand of little rocks from upstream. So that's really exciting. Then, and of course, they're habitable environments of their own. They're river environments. The mud deposits are very nice because rocks like this tend to concentrate organic matter on Earth. And so we think they have very high prospects to preserve organic biosignatures that we might find back on Earth. But also because the slower sedimentation rate out towards the middle of the lake means that you get these fine layers. Imagine what the sediments look like as they pile up on the bottom of the lake. You can pack a lot of geologic time, relatively speaking, into a single sample compared to a faster sedimentation rate up closer to the river. So we like it for its ability to record records of potentially changing environmental conditions in the lake or even potentially changing climate. So the last of the sedimentary units, probably sedimentary units, are these carbonates. So you'll hear us talk a lot about carbonates in reference to Jezero. And this is the detection of carbonate minerals from orbit is one of the key things that led us to Jezero Crater and to this region of Mars, which has the strongest signature of carbonates. Carbonates we love because they're great for astrobiology. They have carbon in them. Carbonate minerals tend to form around organisms on Earth. Many different types of organisms are involved in either the direct precipitation of carbonates or just tend to live in the carbonate-forming environments. They're also very good at preserving biosignatures. On the other hand, from the standpoint of planetary evolution, carbonates record in a little mineral capsule the changing environmental parameters, the changing aspects of the carbon cycle and the oxygen cycle. They can record past temperatures, those sorts of things. So we'd like to sample them from that respect too. And there's two main types of carbonates. Briony will talk a bit more about this. There's carbonates further out into the basin, exposed in one way, and you see those indicated here. And then we're particularly excited about what we call the marginal carbonates, which are there on the margin or the edge of the lake. And so I'll leave this to Briony to talk more about why we are so excited about those. And then zoom back out quickly for the last piece of the Jezero geology, where we look at to the southwest of Jezero. There's this giant volcanic province that we call Syrtis Major. This stuff was erupting sometime between 2 and 3 billion years ago, maybe at a time long after Jezero Lake had dried up. Why is it important to us? Well, it would have been spewing out lava and ash in the direction of Jezero Crater, and in fact, we see a geologic unit marked here with these little sort of triangle symbols that sits on top of a lot of the basin fill in the crater. We call that the mafic crater floor unit. So it has a mineralogy that's consistent with it being an igneous rock, maybe having come out of a volcano. We really like that possibility because if so, and if we can determine that it's younger than all the sedimentary rocks in Jezero Crater, we can also bring back a sample of that and get the age of it, because volcanic rocks are quite easy to date. And so we'd have potentially a sample of the crater rim, giving a maximum age for sedimentary activity in Jezero, and a sample of that mafic crater floor unit giving a minimum age, therefore bracketing in absolute time all that interesting environmental change that we're hoping to study. So that's the basic geology of Jezero, and I'll now turn it over to Briony to talk more about the carbonates.
All right, thank you, Ken. Okay, so I'm going to talk about a specific result that actually came out of our landing site evaluation process on the team, and it's one of the things we're really excited to study in Jezero Crater. But first, we're going to take a step back and move back to Earth. This is a picture I took earlier this year on the shores of the Great Salt Lake, just outside of Salt Lake City. And you can see the lake in the distance, right, sort of back here in the background. And what we're looking at here are these sort of strange mounds on the shore of the lake. These are actually called stromatolites. And what these are basically giant mounds of carbonate that have built up over time due to the interactions with microbial mats that were growing on the shores of the Great Salt Lake in the past. And these are really exciting for astrobiologists because there's this interesting interplay between geologic processes depositing the carbonates and biologic processes growing the microbial mats in them. And so you get this sort of interesting field of what we call microbialite rocks, so rocks that are actually sort of helped to deposited in part by microbial processes. So this is the kind of thing we would love to find at Jezero Crater, right? Because it's a rock that is partially created by microbes, and so this would be kind of the holy grail on Mars to find something like this. And so one of the questions we had going into our landing site evaluation was, okay, could there be something like this in Jezero Crater? Is that possible? The other reason we really want to find something like this is because these rocks, these stromatolite rocks, can help preserve biosignatures over geologic time. So here we're jumping just to the other side of Utah, just a few hours drive away. And here what we're looking at is, in fact, still a stromatolite, but it's been broken open. And here you can actually see, growing from sort of lower left to upper right, how the stromatolite grew over time as carbonate was deposited out of the lake and the microbial mat grew up toward the surface. And you can see it has this kind of really interesting organic-looking texture. It doesn't look like a normal rock. And there's a debate in the community about whether or not the microbes actually create this structure or if it's a purely abiotic structure. But the really great thing about this process is, regardless of whether or not the carbonate itself is deposited by the microbes, that physical act of deposition of the carbonate traps all kinds of biologic materials in the stromatolite itself. So it traps the microfossils of the microbes themselves, their organics, lipids, even isotopic biosignatures. And so it's rocks like these stromatolites, that are some of the best records we have of the history of microbial life on the Earth. And so we would love to find something like this on Mars. And in particular, this one you're seeing here is actually 50 million years old. Now in Jezero Crater, we would love to find something like this, but of course it'd be much older, on the order of 3.5 to 4 billion years. Okay, so then our question was, is there somewhere in Jezero Crater we could go looking for textures like this, right? Things that could be basically a big signal post saying, hey, look here for biosignatures with the rover. So here we are back at Jezero Crater, and here's a slightly different view of the crater, looking at actual orbital data now. And so you can see the gray background showing the crater itself, and then the colors that are on top of that are data from the CRISM orbital imaging spectrometer. And this is the instrument we use to detect minerals from orbit on Mars. And so the colors you're seeing here aren't the colors you see with your naked eye looking at Jezero. In fact, they're near-infrared light that we've turned into red, green, and blue to give you a color image here. But what the colors here are telling you are about the mineral diversity in the crater. And so the greens and reds here actually correspond to those different carbonate deposits that Ken was talking about. So the red here, sort of just beyond the delta, you can see out in the basin, that corresponds to those basin fill carbonates. And then if we zoom in, looking at the delta itself, you can see there's also this kind of bathtub ring of green materials just behind the delta on the inner margin of the crater. These are the marginal carbonates that Ken mentioned. So this, you can tell that they're in fact carbonate bearing. We can tell from orbit that they contain carbonates, but they look different from the rest of the carbonates in the crater that are red here. And so our question was, why are they different? Is there something unique about these deposits? So you can tell already from the color that they're different, right? So what that color is telling us, it turns out the red color that's out in the basin associated with those carbonates is due to the presence of other minerals like olivine, which is a volcanic mineral. And that's telling us that those carbonates are basically mixed in with other minerals. They're just one component of a rock. What's interesting about that green bathtub ring is that the carbonate signatures first are much stronger, and also there are actually locations in there where we only see carbonate. We don't see it mixed in with other minerals. And so that's really encouraging if you're thinking about, okay, if I'm looking for carbonates that deposited out of a lake, I should expect to see pure carbonates or relatively uncontaminated carbonates along a lakeshore. And so that's the kind of signature we were looking for, and we identified it in these marginal carbonate units. Okay, but that's not enough, right? We need to be able to show that the context of these sort of different carbonate deposits makes sense for it to be along a lakeshore. So here now we're going to look at just topography and elevation of the crater. So here we're looking at all of Jezero Crater again. This is an elevation map where blue is low and green and yellow are high. And you can see the marginal carbonates are this filled in cyan area on the left of the crater. You can see the Mars 2020 landing ellipse there as well. And then I've also highlighted two contour lines on this map. The upper one corresponds to the highest lake levels that we think ever existed in Jezero Crater. And you can see they're really high. They sort of run right up to the rim of the crater. But you'll notice that those are actually higher in elevation than this lower line, which corresponds to the lake levels that we think were present after the eastern rim breached to form that big outflow channel flowing to the east. And so the zone in between I've been calling the Shoreline Zone. It's basically the area in which we think you could find preserved shorelines and lakeshore deposits in Jezero. And you'll notice that the marginal carbonates and all this teal polygons correspond really well to that zone in Jezero Crater. And so based on the fact that they fall in this shoreline zone and they exhibit these very strong carbonate signatures, we think it's possible that these could actually be those lakeshore deposits we want to investigate with the rover and look for biosignatures within. So we're really excited to investigate these deposits with Mars 2020. Okay, and now I'll turn it back over to Ken Farley.
So mostly what you've seen so far is some hand sketches and a few analog photos. We want to close with showing you what this site actually looks like. And we are the beneficiaries of an enormous amount of work that has gone before us. And just as an aside, to me, what we are able to do now with Mars is allowing this exponential growth in the kinds of questions that we answer. The first missions to Mars, we're stumbling around in the dark trying to figure out what the planet was all about. And now we are able to ask an incredibly diverse set of questions. And if we manage to bring those samples back from Mars at some time in the future, that exponential increase in our understanding and the questions that we will ask will continue to grow. So with that said, let's start with the movie. So what I want to do is I want to point out some of the, here we go. Some of the features. You see the topography, the colored topography, and there is the Isidis Basin. There are the Syrtis Major volcanics and the location of Jezero Crater up on the side of the Isidis impact. Now you're seeing high-rise imagery draped over the topography that comes from the Mars Reconnaissance Orbiter. And in the blue, you see our landing ellipse. We will land somewhere within that ellipse. And the white line indicates a notional traverse. If we were so lucky as to land in the dead center of the ellipse, we have already identified, based on the detailed information that we have, the targets that we would go to look at. the first thing that you should see when you look at this image is this spectacular delta. This is like out of a textbook of what a delta would look like as water flows into the lake. So as we roll the image back here, you can see the canyon slicing through the walls of the crater. You can picture the water running down that river into a lake that would have been the size of Lake Tahoe. When that water slowed down, it dropped the load of sand and mud that it had. And as Ken said, this is very exciting as a place to prospect for life, because that material that deposits from a lake is both a place where things could live and a place where materials could be trapped and preserved for us to find now 3.5 billion years later. So here we are moving along on the traverse. This is up on the edge of the delta. So we would go along and we would explore the delta, the various different kinds of rocks there, the sand and the mud. Here you see a wonderful modern sand dune field. It's beautiful. The rover would be ill-advised to try to cross that. I particularly like this little stretch here because if you look closely, you can see fossil shorelines that are kind of like what you'd see at the Great Salt Lake. The mission would continue to move up the delta, and it would cross through the area that Briony talked about, the carbonates that are deposited on the shoreline. And then, as it continues along, it would move onto the crater rim, where we see those impactites that Ken referred to, places where we might find hot springs that had things living in them. And then off in the distance, we see this wonderful diversity of rocks that are very ancient, some of the most ancient rocks exposed on Mars. And potentially we can explore those with the material that Ken referred to that is being transported down that river channel, and the little fragments that are in the delta will tell us about that. So this mission is going to go to Jezero Crater to explore this great diversity of rocks and habitable environments. And along the way, we're going to collect about 40 samples and leave them on the surface of Mars. And in the future, hopefully, they will be picked up and returned to Earth. Thanks.
Great. So now we'll open it up to questions. Do we have any questions from reporters in the room? Yep.
Hi, my name is Sid Perkins. I'm a freelancer for Dr. Williford. You talked about the types of rocks in the crater, and one of the things you talked about was volcanic mafic rocks. Is there anything that you can say, you know, from the data that you have about where they are and how thick they may be or whatever, about whether they were washed in and, you know, as you mentioned, integrated from elsewhere in the watershed, or whether that was merely a diffuse ash plume that kind of plopped down in areas?
Yeah. So I guess this mic is on, the light's not on. We have done a lot of work to try to understand whether we could conclusively say this thing we call the mafic floor unit is definitely a volcanic rock. We worked hard to figure that out. I can't say that the case is completely closed. There are a number of observations of we call the geomorphology, just the shape of the rock, that are consistent with it being potentially a lava flow that embayed or flowed up to the delta. But then again, it doesn't show, you know, the full set of characteristics that you might expect from a rock like that. So it's not completely obvious to us that it clearly is a volcanic rock. So it's still an open question, which is great because it's a fun first thing. It's likely to be the first question we start asking in the mission because we're likely to land on that stuff. It's the stuff that mostly makes up the floor of the crater. So it's a great first question for us. Is this a sedimentary or an igneous rock? It's like as basic as you can get in geology. But there's a lot of good evidence pointing to it being volcanic, which would be great for the reasons we talked about.
Bad boys at the back. It's Jonathan Amos from BBC News. If you look at the evidence that's presented here on Earth for very early life. You know, we're talking, you know, close to 4 billion years ago. It is deeply controversial. You know, even with the stuff that we have in the labs and the analytical tools that we're able to bring to bear on those samples, still people argue furiously over what they represent. Is it possible that the evidence that we might get from Mars might be easier to interpret because, you know, Mars kind of just stopped doing its thing shortly after this life, if it is indeed life, was there? Are there processes, you know, the geochemical processes that might mask life here on Earth very early on might not have had the same effect on Mars? It might be easier to determine.
Yeah, it's a great question. So I have two things to say in response to that question. Some of the stuff you talked about in the beginning is some of the work that I do on you know, old rocks on Earth, looking at signs of life. And you're right, that in the oldest sedimentary rocks that we have, it's very hard to get complete consensus agreement on whether something is conclusively evidence for life, even given all of our tools on Earth. This is one of the reasons why the idea of sample return is so powerful for astrobiology, represents such a powerful opportunity, because you can imagine that if we can't agree, you know, here on Earth, when we can go back, you know, year after year to the field site and take our samples to the synchrotron and so forth, how are we going to do it without having the samples in the lab? So to really get a good answer to that key question of astrobiology, I think we need the samples back. But to your other point, a very astute observation, there certainly is, because Mars, as Ken said, it sort of shut down early, and as you pointed out, it shut down early as a planet. A lot of its processes shut down. We don't believe it had plate tectonics in the way that the Earth has had for most of its history. And that is a process that on Earth, as you point out, has driven metamorphism and destruction of a lot of rock. A lot of the rock record is completely destroyed by subduction under the ocean crust. But the rock that's left on the surface is heated and squeezed in ways that it might not have been on Mars. And so it may well be that these rocks that are older than any sedimentary rocks that we have here on Earth really may be sort of paradoxically may be much better preserved than much younger rocks on Earth in certain ways. Now, there are other aspects of Mars when you strip away the atmosphere and you introduce a different radiation environment that work against us from the standpoint of biosignature preservation. But you're right that this is one of the big, broad areas that we seek to understand with 2020 is how are signs of life and planetary evolution preserved on a planet like Mars? How are those preservation processes different on Mars than they are on Earth? And MSL is making a lot of strides in this area, and we hope to follow on that as well.
If I could add just one perhaps obvious follow-on, the other thing that's happened on Earth is billions of years of additional life that is contaminating the ancient rock record. If there's one thing we're pretty confident in, is there isn't life all over the surface of Mars contaminating every rock surface. So that makes it a little bit easier.
And the other thing is what have you learned from MSL Curiosity that will enable you to make sure your choice of sample is a good one? I mean, obviously getting below the surface is important, but what have you learned from Curiosity that will guide your choice of sample, if you can think of it?
I'll let everybody else answer too, but I think one of the biggest things is we are finding organics. We're finding some complex organics, so that's encouraging that even in places that aren't necessarily the best to be preserved because they've been exposed for an extended period of time, we can still find organic compounds. So they're there to find, and then the challenge will be whether or not there's enough information left in the molecule to actually tell you what its source is. The other is that Curiosity within the first year of the mission definitely showed that Mars was at least habitable at Jezero Crater. So we know we're on the right track in terms of looking at Mars and seeing whether or not anything got started on that planet in its first billion years. All the other things, we're learning a lot, but they're very subtle, and I'm not sure if I can call out any other highlights that would be particularly helpful.
I can
dating is one. But.
Well, I can add sort of a technical thing we've learned from Curiosity, and that's how to choose a sample, right? The Curiosity is the first time we've drilled into a planetary surface like that, and we've learned a lot about how do you choose the site you're going to spend that time doing it. And so that's helped to inform, how we'll actually run the rover, the day-to-day operations on the ground. How do you canvass the site? How do you choose this one special rock that you're going to drill and return to Earth? And I think that's been a huge, huge improvement that we've learned over the last 5 years with Curiosity.
And I'll just say one other thing, which I'm surprised Ken isn't saying something about it, is on Curiosity, we actually dated a rock, and we also dated its exposure time. And what that does is it points to an exploration approach where what you'd want to do if you want to find rocks that are relatively new or freshly exposed, you need to go to an outcrop that looks like it's being eroded away. And then if you're able to do that, then in fact you do get rocks that have not been exposed to galactic cosmic rays for an extended period of time. And that, in fact, might have a record in that sample that preserves to some extent what the organic thing that was originally deposited, whether or not it's from meteorites, from volcanic activity, or from potential life itself.
All right, do we have any other questions from reporters in the room? Anyone else? Any questions on the chat? Okay, I think we'll conclude there. Thank you guys so much. We'll reconvene at 1 p.m.
Thank you.
Thanks.
Thanks, everybody.
Thank you.